Welcome to N is for Networking. I am Ethan Banks, your grumpy old network engineer, along with Holly Metlitsky, who's just new enough to networking to not be grumpy in the least. And in today's episode, we cover a listener question going back to episode 2. And in episode 2, we were discussing bandwidth and latency, and the topic of Ethernet lanes in high-speed Ethernet came up, and our friend Matthew H. had questions. He asks, when you talk about channelization and lanes, what does that look like physically? Is it multiple physical cables? How does it compare to LACP? So 40 gig Ethernet is for 10 gig lanes, right? How is that different than for 10 gig links in an LACP group? And I believe with LACP, Matthew continues, if you only have one file being transferred from one server to one client, the max speed would be 10 gig, not 40 gig. With 40 gig Ethernet, if that's still 4 physical cables, would the single file be transferred at 40 gig? The Wikipedia page for 40 gig and 100 gig mentions both 10 by 10 gig and 4 by 25 gig for 100 gigabit Ethernet. Is there a practical difference? Even with an electrical engineering and an IT ops background, that page is difficult to extract anything useful from. Okay, Matthew, today's your day. Let's see what we can figure. We're going to walk through all of this stuff. So, Holly, here we go. Let's start with Matthew's question at the beginning there. He asks, when you talk about channelization and lanes, what does that look like physically? Is it multiple physical cables? And you tell me I'm jumping in too fast.
Yeah, I was going to say, let's take one step back and just, maybe discuss what channelization and lanes mean in this context, because I personally have dealt with channelization more in regards to Wi-Fi. So, when discussing physical cables, let's just describe what that is first, and then we can jump into the rest of it.
Yeah, so channelization in Wi-Fi, I mean, it's not really a parallel thing, because in Wi-Fi, you're talking about a certain amount of radio spectrum that's been allocated to the Wi-Fi system. At 2.4 gigahertz, you've got 11 different channels. And then your radio signal goes across one of those channels and typically spreads out into the adjacent channels. And so you build a channel plan so that the radio communications don't overlap. We're not talking about that here with Ethernet. Maybe I shouldn't say channelization. Maybe the best term is just to say lanes and avoid any confusion here and overlap. And we just stick with the term lanes. I just have the term channels in my head and splitting things up. I think of it as channelization. But for our purposes, we're really thinking about lanes like a highway has multiple lanes for cars. It's more like that. And the issue comes in with Ethernet signaling, and you've got, as Matthew mentioned in his question, the Wikipedia page for 40 gig and 100 gig Ethernet mentioned 10 by 10 gig and 4 by 25 gig to make a 100 gigabit, I was going to say channel, and I'm trying to avoid that word now, but to make a 100 gigabit interface. So what's going on here? What we end up with, you can't, depending on the physical media that you're transferring across, you don't have a 100 gigabit signal that you can send over in one lane. You need to use multiple lanes aggregated together to form a single 100 gigabit signal. And so the folks that were designing 100 gig and then later 200 gig and 400 gig and 800 gig, you're going to see this technique used over and over, are taking signals that they can send, you can send 10 gigabit over a single lane. You can send 25 gigabit over a single lane. And then the standard will combine those lanes together into and result in one interface, what looks to the switch like one 100 gig interface in that case, or 40 gig interface if it was 4 by 10.
I guess I've got a question there. So you talk about the standards and that, maybe they specify 25 gigs. What is the maximum? Maybe again, we need to take a little bit of a step back and talk about the physicality of this, but what is the maximum somewhat single lane capacity? So if 100 gig, can you have 100 gig single lane, or is there some sort of physical restriction on that?
I don't know off the top of my head what the max is. I'm trying to think. I don't think I've seen schemes that go beyond 25 gig signaling in a single lane. I know part of the challenge is when you're working with copper traces as a medium, you're working with light going down a light core. There are limitations on how fast you can do the signaling to send traffic down the line, but I don't know off the top of my head if there is a maximum, like we're coming up to the limits of what technology can send down the line. I don't know. I don't know exactly what that limit is. I do know there are a ton of standards that govern signaling depending on what the physical medium is that is in use. So if you've got copper signal, there's another piece of this, Holly, which is distance. The shorter you go, the more you can cram down the line. That's for sure. So maybe it's possible that you can send 100 gig as long as you're going a very short distance. But the further you go, the less tolerant of errors and so on that signal is. And so you end up having to go a slower speed to make sure that the signal is actually going to get from one end to the other without being corrupted or having some sort of a problem. So when you look at the standards like 802.3AB, 802.3AH, and a zillion other ones that come under the Ethernet 802.3 family, the standards are defining how to get a certain amount of bandwidth down a medium over a specific distance. How are we going to do it? It's copper, it's fiber, it's certain types of fiber, because there's different grades of fiber too. There's multi-mode fiber, there's single mode fiber, and then even within that, there are different grades of the quality of glass and the diameter of the glass that govern how far that traffic can go. All of that coming back to the Ethernet standards folks who are defining what the method is that we're going to use to signal traffic across that physical medium, across a particular distance to accomplish 40 gig or 100 gig or whatever the standard is.
So those standards, just so I can understand this, they help us understand possibly the capabilities within certain limitations. For example, you said over a certain distance, with a certain signal, over a certain wire, to say, okay, well, this is what you have and this is what you can get out of it, and how to get, let's say, that maximum 40 gig from what you have here.
It helps us understand that as consumers of the technology, as network engineers.
Yes.
But it's also, more specifically, I think it really helps the equipment manufacturers. So you've got folks that manufacture cable. Then cables have to be manufactured to a certain standard and a certain specification. They have to know how to make the copper and make the fiber optic cable, the glass that is going to carry that signal. That's a piece of it. The folks that are making an optic transceiver that you would plug into your network switch, that has to comply with a certain standard. Okay, this is Cisco might call it a 100 gig Ethernet SR4 fiber optic module. Okay, that SR4 complies with a certain Ethernet standard and is expecting a certain kind of cable to be plugged into it for it to work right. So that fiber optic module has to conform to a certain spec. And part of the reason is, well, why are there so many specifications? Well, money. It's way cheaper to make a module that can go a very short distance over copper cable than it is to make a fiber optic module that can send traffic many kilometers across a city, let's say, or across a wide geographic region. For a telco that needs to go, I need to connect, 200 kilometer link between these two cities. And so you have to use a very different sort of fiber optic module that's going to cost a lot more to get that signal down the line.
Okay. Yeah, that makes a lot of sense. I guess reverting back to his original question, asking what does this physically look like and how does that work?
So let's dig into how this physically looks for Matthew. So back to the question: when you talk about channelization in lanes, what does that look like physically? Is it multiple physical cables? Kinda. So let's back up a second and talk about what we think of as an Ethernet cable. What do you think of a regular old Ethernet cable, not fiber, just a regular copper cable with an end on it like you'd plug into the wall, Holly? What do you think of when you think of that cable?
I think of a couple copper wires twisted inside.
Hmm.
But maybe that's because I've cut open a couple of them.
Yeah, yeah. Well, but that highlights the point here. We think of it as maybe one cable that plugs into the wall, but actually it's 8 conductors in there. There are 4 different twisted pairs of wire that are twisted around each other to eliminate crosstalk and so on. And different grades of cable like Cat 5 versus Cat 5e versus Cat 6 versus Cat 6e and so on have different characteristics about the conductors that are inside that wire. There could be more twists per foot, let's say. So way back in the day, we had Cat 3 cable, which was good for up to 100 megabits per second Ethernet. And it was very commonly used in lots and lots of buildings. And so lots of specs would be like, okay, we got to get 100 not gig, but 100 megabit per second to be able to run across Cat 3 because so many buildings have this installed. And so there was a lot of work done to make sure that that was a thing that could happen. But then we moved on. And okay, well, 100 meg is too slow. We need gigabit. So 1 gigabit per second was like, you got to have Cat 5 at least, even better Cat 5e. And then Cat 6 and Cat 6e and so on have rolled out. Like my house has Cat 6 installed in it. I could have gone with Cat 6e, but it was a lot more expensive for no particular benefit in my case. So I didn't spend the extra money for Cat 6e. But the more to the point, there's 8 conductors in there in that one wire. Well, in the case of, let's talk about 100 gig Ethernet going over fiber optic cable. This is a very I picked this one because it's very common. Cisco had a great page explaining 100 gigabit Ethernet SR4 fiber optics. They talked about a ton of fiber optics on this page in different modules that they sell. The SR4 one being a pretty common one that they sell. Well, that 100 gig Ethernet SR4 goes over a 12-strand fiber assembly called MPO12. And what's in there are actually 12 strands of glass. It looks like one cable from the outside, like a regular old Ethernet cable that we'd plug into the wall at home or we could buy at a big box store. That's 8 cables inside, 8 tiny cables. Well, there's 12 strands inside of an MPO12 cable that you would plug into your 100 gig Ethernet SR4 fiber optic module. And of those 12 fiber strands, 8 of them are used and 4 of them are unused. And those 8 used ones, you got 4 of them are used for transmit, 4 of them are used for receive. And so I suppose the question then, Holly, is what do you do with the 4 that aren't being used? That could be.
I was going to exactly. Do we know? Is it redundancy? Is it just to maybe separate the transmit and receive cables or strands?
They literally aren't used for anything. There is no purpose for them in this case. But, so why? This is going to come down to some manufacturing question. Like, wait, so why didn't we have an MPO8? Why is there an MPO12 with 4 unused cables for this particular standard? Because reasons. I don't know why. Exactly. But it's not uncommon. Back in the days of going back to, like I was talking about category 3 and category 5 copper cable from way back, you could have a category 3 cable only needed 4 conductors, but you could use an 8 conductor cable and still send fast Ethernet over it, even though two of the pairs would be unused and 2 of the pairs would be used. So it's not like that never happens. That's a thing. There are also beyond MPO 12. There are, I believe, I remember seeing MPO 16 and 24 and maybe 32, where there's just more and more strands of glass crammed into that one sheath. What looks like a single cable, even though there's multiple conductors under there. So Matthew, I hope we haven't rambled too much and confused you, but the idea is it looks like a cable, but if you actually look at what's inside there, you've got multiple strands of glass inside that conductor that are handling the lanes, the different Ethernet lanes. And in this case, this particular standard, we are doing 4 by 25, 4 transmit and 4 receive. So you got 25 gig lanes that give you a 100 gigabit Ethernet interface. That's what it looks like. Now, another thing I wanted to point out is the color of the sheathing on that fiber optic cable assembly matters too. That can tell you something interesting. Some of them are yellow, some of them are orange, some of them are like a light blue, like I think they call it cayenne. And those all indicate the grade of the glass that's inside. And depending on the grade of the glass, you may have distance limitations. Oh, this grade only goes this far. This grade goes further. And that's just one of those things. We're not going to break all those out now because I don't remember them all in my head, honestly, anyway.
I definitely have a list of that somewhere.
Yeah. Well, it's something you'd have to know, like in your job, Holly, you'd need to, if you had to spec cabling assemblies, you might have to know, like, well, how far between your switches in your data center or in your building are you going? 150 meters. Oh, okay. Well, that means we need to spec this specific kind of cable to make sure that we can go safely between those two switches. So you care about that stuff. You begin when you start doing design work for laying out a network inside of a building or inside of a data center. You have to understand all that stuff and know. Again, because a lot of it goes back to cost. It's not just so that you can make the connection, because you don't want to overspec this stuff. You don't, why would you spec the most expensive kind of fiber optic cable if you're just going rack to rack in the same row where your maximum distance is like 5 meters? Well, no, you'd spec a cheap copper cable assembly in that case to save money, because all this stuff adds up. And when you're doing a big data center build with dozens, hundreds, or maybe even thousands of switches with that many more interconnects between them, wow, you got to get the price under control. Yeah. So you want to spec the right thing to go in between these devices in that data center or that building. So Holly, one other point I wanted to make about this are breakout cables. Now, have you run into breakout cables in your world?
I have indeed. Usually in the context where a customer would want to buy a certain switch that, for example, a data center, you really want those 100 gig, 80, 25 gigabit ports, but you have one little something that needs 1 gig or 10 gig. And it doesn't make sense to buy a different switch or to buy a smaller box. So instead, you can break up one of those 25 gig ports with a breakout cable to smaller lines to connect multiple things to that one port.
Exactly. And so Matthew, just to confuse you even more, that's the challenge here is we described the Ethernet lanes, and we described how the ports are interconnected, and you're really dealing with, say, 4 25 gig lanes or 10 gig lanes, all depending on the spec of the fiber optic module and the kind of cable that you're using between them. But you can put a port into a breakout mode where that 100 gig port actually presents as 4 25 gig ports or 10 gig ports. Or more. You can do, there's other kinds of breakouts as well. And so you end up with this spaghetti looking thing where it's like it plugs in as 100 gig on the one side, just a single plug into the fiber optic module. You've configured the switch and said, hey, I don't want this to be a 100 gig port. I want you to treat this like it's 10 gig ports. And then the cable assembly breaks out. It fans out into 10 gig links on the other end. And that's a design question, because exactly like you said, Holly, is there a need we have on the far end for this one host that can't talk at the higher speed to talk to the lower speed, and we don't have a lower speed port for them to plug into? Okay, put the switch port, that high speed switch port, into that breakout mode, and then use a breakout cable to fan out and get a bunch of connections that way. It can be really clunky cabling in the closet itself, in the rack. It's a thing. You gotta manage all that spaghetti. But
yeah, I wouldn't say they are a go-to. It's more of a really need basis. It's not really preferable to have 101 breakout cables. You buy a giant box and separate all of your ports. It's not pretty.
Right. I agree, but it's one of those things. If you need it, you need it. And okay, well, let's move on to the next part of Matthew's question. How does lanes and channelization, how does this compare to LACP? And Matthew, you described it this way: 40 gig Ethernet is 4 10 gig lanes, right? Yep, that's what we were describing. And we were describing 100 gig as 4 25 gig lanes potentially. There's other scenarios as well. Well, how is that different from 4 10 gig links in an LACP group? I believe with LACP, you have one file being transferred from one server to one client. The max speed will be 10 gig, not 40 gig. Right. Okay. So let's talk about LACP. Holly, have you worked with LACP?
Yeah, I have indeed. So LACP is Link Aggregation Control Protocol. So it lets you bundle several physical interfaces into one logical interface, which will lead us into possibly our next topic, which would be LAG, Link Aggregation Groups. And it's quite a common use of this protocol.
And so, Matthew, when you're doing LACP like this, there is a distinction between the way LACP forwards traffic across each link member and the way Ethernet forwards traffic across a lane. So there's another point here to make that we haven't made yet, Holly, which is if you're a network engineer and you're dealing with a 40 gigabit per second Ethernet port or 100 gigabit Ethernet per second port, you don't actually have to care about the lanes underneath. How it works is incidental. It's like, if you want to know, cool, let's talk about it. But it's not like this impacts your world a whole lot unless you're doing something unusual, like a breakout cable, kind of a one-off scenario. But okay, let's talk about what the differences are here. But just so you know, this isn't a day-to-day thing that's going to weigh heavily upon you as you're configuring switches. It typically is not.
No, this is my first time discussing lanes in that context. I understand the gigabit Ethernet that I need and possible breakout cables, but I've never thought of it at this granular level, it's very interesting.
And it's about to get more granular, but let's talk about LACP first. So to answer your question, Matthew, you said, hey, if I've got two servers on either side of an LACP group, let's say for 10 gig interfaces that are giving me a total of 40 gig, the maximum speed I'm going to get between those two servers is 10 gig, right? Right. Well, why is that? Well, the answer is the way LACP forwards traffic across it, it doesn't forward like one Ethernet frame in a round robin fashion where frame one goes to lane one or link one, and frame two goes to link two, and frame three goes to, it doesn't do round robin like that. And the reason it doesn't do that is out of order packets are bad. And so you want to make sure that that your traffic arrives in order. And so it's best to make sure that the entirety of a conversation between two hosts goes across the same lane, or the same link in this case, I should say, link aggregation. It goes across the same link in your LACP group so that your traffic arrives in order. If traffic arrives out of order, you're confusing the receiver, where the receiver's like, wait, I got packet 3 before I got packet 2, and it has to reorder the packets, which, depending on the IP stack that's receiving it, it can maybe handle that, but maybe it can't handle that, and it blows up the whole conversation, and it's, generally speaking, a bad thing. LACP then, when you're dealing with an LACP group between two switches, the switches are like, okay, we're going to avoid the out of order thing. We don't want to have out of order packets. So we're going to look at the characteristics of the flow between these two hosts and do math, compute a hash to determine which member of the LACP bundle we're going to send that conversation across, which then means now you're throttled to the maximum bandwidth of that one link. In this case, in Matthew's example, 10 gigabits per second. So you're exactly right. We can get more into hashing. In fact, we're going to. Holly and I are actually planning to record more about this later today. Although to you listening, it's going to be episode 11, I believe. But we're going to be talking about LACP, multi-chassis link aggregation. We'll get into hashing a bit more and so on. But for now, understand that as far as how LACP works, Matthew. Now, Ethernet lanes don't work like this. So an Ethernet lane, what's happening under the hood is if you do a search, if you want to dig into this, do a search for PCS. PCS. I've got to remember what that looks like. Hang on a second. Physical coding sublayer for Ethernet is what's happening deep under the hood of Ethernet. Physical coding sublayer and the physical medium attachment, PMA. So PCS and PMA. So down in the guts of Ethernet, as it's trying to signal from one end to the other, you've got these subsystems, the physical coding sublayer, the physical medium attachment. And if you get really deep and nerdy into how Ethernet is doing what it's doing and looking at the lanes and so on, there are documents out there that will explain to you exactly what's going on way down at like an electrical signaling level. In a nutshell, what's going on here is the PCS is going to break Ethernet frames up into code words. A code word of 66-bit blocks is the reading that I've done so far. And I am not an electrical engineer. I don't do Ethernet standards. So this may vary from Ethernet standard to Ethernet standard, but just the reading that I've done. For 40 and 100 gig, you get frames broken up into code words of 66-bit blocks. And then each 66-bit block is sent round robin style across the Ethernet lanes in parallel. So instead of a hashing mechanism where it's like, okay, this conversational flow is going to get stuck to one link group as in LACP, you end up with, I've got bits coming at me. I need to translate into electricity or fiber optic light. How am I going to do that? Well, I'm going to break all of this up across the lanes, my 425 gig lanes, let's say, or my 410 gig lanes to go 40 gig. 66-bit blocks, one block across each lane, send them in parallel down my lanes. And on the other end, those 66-bit blocks are reassembled into frames and sent on. And it's all happened down in the guts of the transceiver that is sending that information. You as an engineer don't see that, don't know what happened, don't have to care. It is the job of the Ethernet transceiver to do that for you. To you, as you're looking at the Ethernet switch, you just see a 40 gigabit per second interface. That's all that's happening. Everything that the signaling that's happening to get traffic from point A to point B, from one Ethernet fiber optic or copper module to the other, and how it's doing that signal and how it's breaking things up into lanes, 66-bit blocks and sending them across the fiber, you don't need to know other than you're a nerd and it's interesting. There's a little more to it because that's like, okay, well, these 66-bit blocks, we got to get them from point A to point B. How do we know on the other end that they arrived correctly and as expected? Well, there's markers that they put in. There are some lane markers inserted periodically and so on. That scheme of breaking Ethernet data up into blocks and shipping them in parallel across the lanes means you're going to get the full interface bandwidth as opposed to being bottlenecked by a single lane because all your data is spread evenly across the lanes. How'd I do, Holly? Does that make sense? Are you nodding? We're on Zoom looking at each other. Are you nodding in a good way or is that what's confusing?
I think, that part, as you said, I'd really, as a sales engineer, don't really have to care about. And I don't think I want to. It gets very, the deeper you get, the scarier it gets. But I just want to go back to LACP. I had a clarification question around there. So in my career, I guess, I've really used LACP more as for redundancy purposes usually. So that, your content has two options, two ways to go in case a link goes down, it can go through the other one, etc. So I guess in comparison to it, we're talking about Ethernet lanes versus LACP. And to me, they're a little bit different. One is you're looking at, the physical transport of data in a cable, where LACP is more of a high level protocol. We've got a set cable. The cables are set. It's just more of what is your purpose for using this protocol specifically. So logically speaking, with LACP, if you've got, your 10 gigabit Ethernet and you are aggregating two links, you're still working with 10 gigabit Ethernet. Your speed is constant, but maybe you can push more data possibly. But
you can, yeah. Yeah, the hashing will
so
give
that's
you
kind
a
of where
rough distribution across your link members.
Yeah.
I agree that LACP redundancy is one of the uses for it. We're going to talk about this more in episode 11, but avoiding spanning tree blocking so that a redundant link is idle is another use case here. You still be running spanning tree, but with an LACP scheme and with multi-chassis link aggregation, you can actually make spanning tree kind of your fallback as opposed to the thing you're relying on for your redundancy. It'll be there to help prevent loops if things happen, but you don't have blocking anymore, where in a default spanning tree system, there's got to be something blocking to stop the loop, since Ethernet does not handle loops. But yes, redundancy, absolutely. Increased bandwidth, absolutely. You do get an increase of bandwidth. It's just not linear, because it all depends on the nature of the traffic that are flowing in between the two switches across that LACP link. What actual throughput you're going to experience depends a whole lot on your traffic mix in your data center and your campus, as far as that goes. All right. So Matthew, let's go back to your questions here. We're working through this with 40 gig Ethernet. That's still four physical cables. Would the single file be transferred at 40 gig? So we described the cables earlier. It is multiple strands of glass, let's say, if it's fiber optics. But yes, the file would be transferred at 40 gig. Now I'm going to put an asterisk here. The Ethernet links are capable of sending at a full 40 gigabits per second. So the question is subtly different. Can the server actually fill the 40 gig link, or can the network devices on either end actually fill the 40 gig link? And the answer is it depends. If you're working with, some servers have a really long life. If you're sitting on something that's 10 years old and you stuff a 40 gig card in it, can it fill 40 gig? I mean, it depends. Can the PCI bus actually handle that? Can the disk drive subsystem in there, if you're streaming off of a disk, actually fill 40 gig per second, and so on? So I wouldn't want you to think that if you aren't filling 40 gig, that the problem has something to do with lanes under the hood. No, it won't. There's a bottleneck somewhere, though, that you might have to track down, but it probably doesn't have anything to do with the network. It's more likely to be in some other subsystem in the systems that are talking to one another across that network. You're 40 gig capable. You can fully fill a 40 gig Ethernet link from a standpoint of Ethernet, but can the servers on either end actually fill that link or not?
So that 40 gig Ethernet, I know Matthew said, is that still 4 physical cables? But in theory, that would be one cable with multiple strands inside.
That's right. Yep. It's going to look like it's going to appear to us as one physical cable. You're not going to know.
Yeah.
You're not going to know. No, it doesn't. Exactly right. Yeah, exactly right. You're not going to know. Like we were talking before about that MPO 12 that's got the 12 conductors in it. 8 of them are hot, 4 used for send and 4 used for receive and 4 unused. Yeah. But it looks like one cable. Exactly right. Exactly right. Although it's cool if you look at the end of it and if it's a live cable, don't stick your eye in it. You'll shoot a laser in your eye and that's bad. But if you actually look at the end of it, you can see the ends of the glass sticking out at the end of an MPO 12 assembly. Yeah. Matthew's last question, and we're going to wrap up this podcast here. The Wikipedia page for 40 gig and 100 gig mentions both 10 by 10 gig and 4 by 25 gig for 100 gigabit Ethernet. Is there a practical difference? No, not from a performance perspective. There's no practical difference there. Whether it's 10 by 10 or 4 by 25 to make up the 100 gig, it's not difference. From a cabling assembly perspective, yeah, there's going to be some kind of a difference there. And that gets into what we were talking about earlier, Holly, with the different standards and the different cables and how far you're trying to go. And all those standards exist to accommodate a budgetary requirement and a cabling requirement. What kind of cable have you got? This is something I kind of mentioned it, but it's worth pointing out again. A lot of data center operators want to reuse their existing fiber optic cabling infrastructure because it's not cheap. And so a lot of the standards exist so that you can get the speed you're looking for across the cable you already have. That's a piece of the puzzle here that I think is an important one. When people are doing network refreshes, they don't want to have to recable everything. That's like really,
Yeah.
I got to recable stuff. And if you're building data centers, like I've been involved in a few data center builds over my career, you make cabling choices and try to future-proof. You put cabling in because it's going to cost a ton to put this cabling infrastructure in place. You want it to last a long time. And then, 5 years down the road, you're refreshing your network equipment. If the vendor's telling you, oh yeah, to do this, you got to completely rip out all your cabling. No? How about no?
Yeah,
Is that a
pretty
good
much.
answer? Well, Holly, how'd we do? What do you think?
I think this is great. I've definitely learned new things about lanes and fiber optic strands, all sorts of granular stuff that I haven't really had to think about yet, but it's great to have this level of understanding. So exactly that, when I'm speccing cables, I actually understand why I'm making certain choices, not just,
Yep.
oh, you want 40 gig or 100 gig. So it's great.
Okay, so looking ahead, if you're interested in this topic and want to go a little deeper, we're going to be talking more about this, focusing on multi-chassis link aggregation, getting away from the Ethernet specifics so much, but more. That's coming up in episode 11. If everything stays on schedule, episode 10, the one you're going to hear next week, we're going to be talking about IPv6 and why we're using colons. We have a special guest coming up for that one. And then MLAG in episode 11. So, all right. Thank you for listening to NS for Networking today. If you have a question or a comment, you want Holly and I to dig into some topic, would you let us know at packetpushers.net/follow-up? Just fill out the form and pick NS for Networking off the list and tell us what you want us to dig into, and we'll dig into it for you. And we got a special request for you. If you're a fan of this show, would you do us this favor? Tell a friend about NS for Networking. That'd be great. Or if you're maybe you're active on social media, you're out on LinkedIn, you're on Blue Sky, are you still on Twitter? Maybe you're on Twitter. Anyway, would you share the show on your social media, wherever you're at? Just let people know that you're listening to it and you like it. We'd really appreciate that. And another thing that would help out, would you leave NS for Networking a review on Apple Podcasts or wherever it is that you listen? Just leave us a quick review, what you think. And those let the algorithms know that NS for Networking out there, and it's likely to percolate up. And other people will discover the show. We'd really appreciate that. Those things are going to help grow the show. There's lots of you listening already, thousands of you. We do appreciate that, but we would love more people. I have been Ethan Banks, along with Holly Metlitsky. You can find us on LinkedIn or the Packet Pushers community Slack group. And just remember, networking isn't hard. Other people figured it out, so you can too.